Cross-bridge cycling is a 4-step repeated process. Attaching the myosin head to the actin, step 1, that is forming the cross-bridge. Step 2 is the power stroke, pulling thin filament by moving of the myosin head. Step 3, release of the myosin head from the actin. And step 4, reset back into the ready to go position. Now, these words go with the next slide, which has a really good graphic, so I'm going to move on to that. All right, so we've already looked at this. The calcium that was released from the sarcoplasmic reticulum binds to the troponin. Troponin changes shape. That moves the tropomyosin off the actin binding sites. Okay? Now, actin down here is already in what we call the cocked or ready position. Okay? So that means it is ready to attach to actin as soon as the binding site is open. Now, when it does so, it forms what we call a cross bridge. So you can see here the head of the myosin is attached to the actin, forming the cross bridge. Now, although it's not shown in this first image, there is an ADP and a phosphate attached to that myosin head. That simply means we have already broken that ATP down and used the energy that was released to get that myosin head into the cocked position. Okay? Now, once that happens, we move into the power stroke. So after forming the cross bridge, the myosin head swivels, and we call that the power stroke. That swiveling pulls the actin filament just a small little distance down past the thick filament toward the center of the sarcomere. Okay, so you can see right here. This is the power stroke. It pulls the actin. Now, that's if we go up here and look at this image of the sarcomere, that's happening here, but it's also happening here. So think of it as if you've got your arms flexed in front of you. So like you're holding up your two fists and you're going to box somebody in the nose, right? Well, now imagine instead of being straight up, lay them out to the side a bit so they're at more of a lower angle, okay? So now your fist should be pointing to the left and the right. Now, bring them right back to the center like you're going to punch your own self in the nose. Don't hit yourself though. Now, that's the power stroke. So we go from back here in the cocked and ready to go position to bang, pull toward the middle. And when that's happening on each side of that sarcomere, that results in the sarcomere shortening. Now I've got a video I'm going to show you. So compare this, the relaxed sarcomere, to here when the power stroke has occurred. Okay? Now the next step is the release of the myosin head. So during that power stroke, we drop the ADP and the ADP and the phosphate off the myosin head. Once it's dropped, that binding site is open again. Well, another ATP is just going to run right in there and hook up again. So when that ATP binds to the binding site, think of it being like a heavy weight. It causes the myosin head to release its hold on that actin. So it breaks the cross bridge. And then the ATP gets broken back down into ADP, and the energy released puts the myosin head back in the cocked position. And if calcium is still present and the binding site is still open, this just continues to happen over and over and over. So it's a repetitive action of these 4 steps that result in the sarcomere shortening, and that sarcomere moves from its relaxed state into the contracting state. Bam, you just contracted a muscle. And of course, this slide just gives you a little bit better view of that. And I really like the way that they put the biceps brachii in here with that. So looking at what happens to the muscle itself. Okay, so when the muscle is relaxed, the actin and the myosin are not attached. The binding site is covered. The elongated sarcomere here has not contracted. Now, if we look right here, we have contracted the biceps brachii. Now let's look at that sarcomere. You can see we've got myosin heads attached to the actin. The actin has been pulled toward the center of the sarcomere. The sarcomere has shortened during contraction. Now remember, if you are in my class, we don't care about the H and the I and the M's and all that other stuff, but you need to know about the sarcomere extending from Z disc to Z disc. Muscle paralysis is simply the inability of muscles to be able to contract, and it can occur if the nervous system function at the neuromuscular junction is not functioning properly, or if excitation coupling is impaired. So this damage can be the result of neurotoxins. Those are simply toxins that damage the nervous system components of the neuromuscular junction. So two paralysis conditions that are caused by toxins are tetanus and botulism. So we'll start with tetanus. It is a form of spastic paralysis caused by a toxin produced by Clostridium tetani. So it blocks the release of a neurotransmitter that results in motor neurons of the muscles it results in overstimulation of the muscles because this neurotransmitter is inhibitory. Normally, it would stop contraction. Okay, well, if you block the release of something that stops contraction, then obviously too much contraction can occur. So it's overstimulation of the muscle cells. Penetrating wounds that are contaminated with soil and vegetable matter are very prone to developing these types of infection. It is life-threatening, which is why you should get a tetanus vaccination to help prevent this from occurring should you be infected with the neurotoxin. Botulism is also a neurotoxin, and it is a potentially fatal muscle paralysis. So it's also produced by Clostridium, but not tetany. It's Clostridium botulinum. So this prevents the release of acetylcholine. Well, if you don't release acetylcholine, then what happens? Muscle paralysis. So this also is very common in the environment. Most cases of botulism result from eating spoiled foods, especially canned foods that weren't processed at high enough temperatures to kill the botulism. Ingestion of honey, unpasteurized honey, in infants during their first year of life can also result in the botulinum spores getting into their gastrointestinal tracts and development of botulism. Now, the FDA has approved the use of the botulinum toxin called Botox Type A for temporarily diminishing wrinkles. So the injections are done in the area, and it paralyzes the muscles in that particular area. So it's also used to help reduce overcontraction of muscles, such as conditions like cerebral palsy or MS, or if you have a stroke or spinal cord injury. So Botox injections last usually about 1 to 2 weeks, and if it is used for muscle spasms, it can last up to 3 to 6 months. All right, let's see. So if you're using it for wrinkles, again, it does have to be repeated because it is not a permanent fix. It is a temporary muscle paralysis.